Alrighty, welcome to lecture. We're going to continue our journey through chapter 7, talking about solution chemistry. And actually, sorry, hang on one second. I think I left the window open. I can hear my the mic is picking up the neighbor's kids in the background. Give me 1 second here. All right, there we go. Okay, so solution chemistry. So on Tuesday, we were talking about, we started talking about solubility, what affects solubility. That'll be a continuing theme this evening. But before we start talking about solubility rules and what affects solubility, we still have a few more nomenclature, items of nomenclature to hash out. The first of which is something called solution saturation. All right, so a saturated solution is a solution in which the maximum amount of solute has been dissolved. All right, that is the definition for a saturated solution. Every solute has a max solubility in any given solvent, and a saturated solution has that maximum. So Tuesday, last lecture, for example, we talked about how 1 gram of water can dissolve a maximum of 0.36 grams of sodium chloride. That would be a saturated solution in sodium chloride because it's dissolved the maximum amount. Likewise, we said that 1 gram of water could dissolve, let's see, 0.0000002 grams of silver chloride, and that would be a saturated solution of silver chloride. So saturated solution, the actual amount of solute dissolved depends upon two things: the solute and the solvent. But the definition is you've dissolved the maximum amount, and that's a saturated solution. An unsaturated solution is it's simply a solution with less than the maximum amount of solute. So you've got the maximum amount of solute. Anything less than that is an unsaturated solution. So this covers a wide range of things. Technically, pure water is an unsaturated solution because it's less than the amount. Well, I guess technically not, because it's not a solution. It's just a pure liquid. So I take that back. But any amount of solute that's less than the maximum would be an unsaturated solution. The third type of solution that you should be aware of is something called a supersaturated solution. Oops. And a supersaturated solution is a solution with more than the maximum solute. All right, more than the maximum solute. Now you may be wondering how. The definition of a maximum is it's the most. So how do you get a supersaturated solution? How can you get more than the most? And then wouldn't that be the new maximum? And the answer lies in some of the concepts we were talking about last class with how temperature or for gas pressure can affect the solubility of a solute, right? So last class we talked about how increasing temperature or adding heat increases solubility. All right, adding heat increases solubility. So the way you create a saturated solution is step number one. You heat the solvent. Step two, you dissolve, or you I should say, you create a saturated solution at the higher temperature. All right, and then step three is you slowly cool the solution. All right, and as you slowly cool the solution, the amount of solute, so you cool the solution down to room temperature or whatever, and the amount of solute now exceeds the maximum amount for the lower temperature. All right, so that is how you create a supersaturated solution. Basically, raise the temperature, create a saturated solution at the higher temperature, and then when you slowly let it cool, the amount of solvent isn't going to change. It's going to stay at the amount that you dissolved. But then the temperature is now lower, and you have a solution with a higher concentration than the maximum amount because it's a saturated solution for a higher temperature. Excuse me. So that is how you create a saturated solution. And again, these are the three types of solution. There is the saturated solution, maximum amount, unsaturated solution, less solute than the max amount, and then supersaturated, which actually cheats the system, exceeds the maximum amount at a given temperature. I should probably add that right here. It's more at a given temperature. Okay. So, now that we've talked about the different types of solutions and the different types of, saturated, unsaturated, supersaturated, we're going to discuss something called the solubility rules. And specifically, if we're going to be explicit here, we're talking about the solubility rules in water. All right, so this is the solubility of various ions in the solvent water. All right. I definitely recommend you add this to your exam sheet because you'll be asked questions about, I'll give you an ionic compound and ask, is this, soluble or insoluble in water? And you'll have to make the determination. So there are 4 categories of ions that we're going to look at. Always soluble, usually soluble, so soluble with some exceptions, usually insoluble, and always insoluble. All right, so let's start with always soluble. So I'm going to write these rules out, and then we'll get some reps in, some practice. So the always soluble ions are the following. Lithium, potassium, sodium, ammonium, and acetate. And nitrate. All right, if you have any of these ions in your compound, it's automatically soluble. All right, now usually soluble are ions that are almost always soluble, but they're insoluble with a few notable exceptions. So chlorides, bromides, and iodides are going to be soluble unless these are insoluble when paired with silver 1, lead 2, and mercury 1. All right. When you pair chloride, bromide, or iodide with silver 1, lead 2, or mercury 1, they are going to be insoluble. Likewise, sulfate is usually soluble, but it is insoluble. It has some notable exceptions. It is insoluble when paired with calcium, strontium, barium, silver, and lead 2. So sulfate is almost always soluble unless it's paired with one of these ions. Then it will be insoluble. All right, now we have our always soluble, usually soluble. We also have our always insoluble. Our ions that are always insoluble are carbonates and phosphates. And then our ions that are usually insoluble are hydroxide and sulfide. If you pair these with anything, they will be insoluble, with the following exceptions. They are soluble when paired with calcium, strontium, and barium. All right. So, something that you should know, that if an ionic compound is soluble, that means that it will be in the aqueous phase. And if a compound, an ionic compound, is insoluble, that means that it will be in the solid phase. All right, that's what it means to be soluble. You're in the aqueous phase, you're dissolved in water. If you're insoluble, it means you're just a solid. Now, I have a question. So we said that if you take any of these always soluble ions, pair it with anything, it'll be soluble. And if you take one of these always insoluble and pair it with anything, it'll be insoluble. What happens if you take, what happens if you take an always insoluble ion and pair it with an always soluble ion? What happens? Because the always soluble is always soluble, but the always insoluble is always insoluble. Who's going to win? The same thing happens here that happens when an unstoppable force meets an immovable object. The object moves because the force can't stop. Just like that, soluble always wins this tug of war. So if you pair an always soluble ion with an always insoluble ion, together they'll be soluble. Likewise, if you pair a usually insoluble ion with an always soluble ion, these two will come out soluble. So solubility wins, trumps insolubility. So just know that when you're pairing and determining soluble or insoluble. All right, we're going to do a few examples where we take these solubility rules that we've learned and apply them to real situations. So I'm going to give you ionic compounds, and you are going to make the determination, are they soluble or insoluble? So determine soluble or insoluble for and then I'll give you All right, let's determine it for lithium. Oops, I want to do this in black. Lithium sulfide. All right. Now, here's the deal. You'll notice that our cation is under our always soluble list, and if you score any ion that's on that always soluble list, it doesn't matter what it's paired with. It's automatically soluble. All right, because an always soluble ion will be soluble whether it's paired with a usually soluble, usually insoluble, or always insoluble. The solubility wins. So we don't even have to look at the other thing. Lithium sulfide will be soluble because lithium is always soluble. Let's do another example. Let's look at barium iodide. All right, now this one's takes a little more thought. You'll notice that barium is not in the always soluble list, so we don't have anything here. So we don't have an instant win. We don't have an instant kill here. Iodine is in the usually soluble list, so when you get a usually soluble, that means it will be soluble unless it's paired with one of its insoluble partners. And barium is not mercury 1, lead 2, or silver 1. So this thing is soluble. All right. Let's do another example. Let's do this guy. All right. Now, again, nothing in the always soluble range, but we do have, bromide, usually soluble unless it's paired with, oh, hang on a second. We actually have one of its insoluble partners. And you'll notice that, because it could be soluble with a different cationic charge, but here this is lead 2, and we have 2 bromides balancing, so that means we're dealing with lead 2 here. So this is our first insoluble example. All right, that would be insoluble. Let's do another example. Ammonium chloride. First thing you want to pull out is ammonium is on the always soluble list. So this thing is soluble. Anytime you get one of those, you instantly know the answer. All right, how about we throw a curveball here? Why don't we do iron 3 hydroxide? Now, this problem is designed to make you freak out, and many students will. Many students do. Many students will. If you're watching this video right now, I know 9 of you are, you will avoid the freak out if you remember how I handle this. Let's talk about why students freak out. Students freak out for this situation because because you'll notice that iron is not in the solubility rules. Iron's not. It's nowhere. And so students are like, what the heck's going on? He didn't tell us about iron. How can we be tested on iron? And here's the cool thing. If you run into a scenario, and I guarantee you will on the test, where you don't recognize one of the ions from the solubility rules, that means that you have the ability to determine solubility based completely on the other ion. So let's look at the identity of the other ion. The other ion in play is hydroxide. Hydroxide is usually soluble. Hydroxide is usually insoluble. Hydroxide is insoluble unless it's paired with calcium, strontium, barium, of which iron is neither. So because hydroxide in this compound is not paired with calcium, strontium, or barium, that must mean that it is insoluble. And it is. All right? So if you see something that you don't recognize from the solubility rules, you now know that I'm testing your ability to look at the other ion and make your determination based on that other ion. And I promise you, you will be able to every time. All right? So now you have armor. See, like, I'm going to be tricky on the exam, but I'm not actually being tricky because I just told you how to beat my trick. All right? So that's my gift to you who are watching this lecture. Let's look at another couple examples. Let's do silver nitrate. This one's a one and done. Nitrate, always soluble. So this thing's soluble. That's all there is to it. All right, how about another one? Oh, this one's a good one. Let's do calcium sulfate. All right, calcium sulfate. So first off, you'll notice that sulfate is usually soluble. It's insoluble when it's paired with, oh, hang on a second. It's insoluble when it's paired with, okay, calcium's the first one on this list. So calcium makes this thing insoluble. Hopefully, also by now, just to point this out, you're getting a feel for why you want these solubility rules on your exam sheet. Because I'm going to be asking you, I'm just going to be giving you, determine whether this is soluble or insoluble in water. And I'll give you a list of ions, ionic compounds. And so you'll have to make these determinations. And if you have these things written out, you don't have to memorize them. You can just go through the list, find them, make your determination. All right, what about... All right, I got two more examples. The first one is again something scary. Students will look at this and flip out because I didn't tell you anything about chromium. Remember, if I didn't tell you anything about the first one, then I'm testing on your ability to look at that second one and make a determination. Carbonate is always insoluble. It will be soluble if it's paired with one of these, but it's not. It's paired with chromium. So because carbonate is paired with chromium, not soluble, this thing is insoluble. All right, one last example. Then we can move on. So, here it is. Nickel chloride. Again, there's no nickel in any of the solubility rules. Chloride, however, is usually soluble. It's only insoluble with one of these three. Nickel is not. So this compound will be soluble. All right. So those are the solubility rules. That's how you make your determinations. You analyze both of them together, sometimes just one. But you'll always, with this information, be able to get to a determination of soluble or insoluble. All right. So at this moment in time, we know a little bit about solutions. We know a little bit about determining whether an ion will be soluble or insoluble in water. We know a little bit about different types of solutions. So, for example, if I said, could you prepare a solution, a saturated solution of sodium chloride? You, based on what we've discussed, know that a saturated solution of sodium chloride has 0.36 grams of sodium chloride in 1 gram of water. So you know to make exactly that, right? You know to put 0.36 grams of sodium chloride, dissolve that in water, or saturated. If I said make an unsaturated solution of sodium chloride, it could be anything, right? It could be 0.35, it could be 0.23 grams. I haven't been specific. Saturation has a definition, but unsaturation could be almost saturated. It could be not even close to saturated, right? There's this huge dynamic range, all right? Now, the ambiguity, the problem of this ambiguity with unsaturated solutions and not knowing exactly how much solute is dissolved in the solvent gets cleared up with the concept of concentration. All right, now concentration, which I'm just going to be abbreviating as conc from here on out, not cronk from Emperor's New Groove. So concentration concentration is a ratio. There's a bunch of different types of concentration units. We'll be getting into them. But the thing to keep in mind is it's simply, at its very core, concentration is just a ratio. It is an amount of solute over an amount of solvent, or there's two formulations that concentration will take. It's either a ratio of the amount of solute to the amount of solvent, or it is a ratio, the ratio of an amount of solute over an amount of solution. All right, those are the two formulations that concentration will take. And we'll see examples that use each different one. But at its heart, it's just a ratio. Solute to solvent or solute to solution. All right, now let's get into some specific concentration units. The first that we're going to talk about is percent mass. All right, this is often abbreviated like so, percent, or at times you'll see it as percent W to W. That's just percent weight, but percent weight and percent mass are the same thing because this is all being done in at roughly the same position in the Earth's gravitational field. So percent mass you'll see abbreviated like this or like this means the same thing though, percent mass or percent weight. But it's going to be the same thing. Now the equation for the percent mass, or sometimes it's called mass percent, highly recommend you write this down in your equation sheets. It is equal to the mass in grams of solute over the mass in grams of solution times 100, right? That's what makes it a percentage. And it's worth noting that the denominator here is solution. So the mass of the solution is equal to the mass of the solutes plus the mass in grams of the solvent. All right, that's something to keep in mind. That mass of solution is equal to the grams of solute plus grams of solvent because it's the solution. It's solvent and solute together. All right, that is the definition of, mass percent. And we can use this information to solve examples like the following. A saturated solution of aqueous sodium chloride has 0.36 grams of sodium chloride dissolved in 1.00 gram of water. What is the percent mass? All right. Well, we know that percent mass is equal to the grams of solute, which is sodium chloride, over the grams of solution. And we're not explicitly given the grams of the solution, but we do know that grams of solution are equal to grams of solvent plus grams of solute, and we have been given both the mass of water and the mass of sodium chloride. Oh, and let's not forget, we gotta multiply this by 100. Oops. All right, so we have both of these values, so we can calculate our percent mass. Grams of solute is 0.36 grams of sodium chloride over 1.00 grams. We can actually, I don't need to include the NaCl part, plus 0.36 grams times 100. All right. So here we got to bust out, or I have to bust out my calculator because I can't do this in my head. 0.36 divided by 1.36 times 100. So my calculator is telling me that my answer is 48.96. Based on my significant digits, I'm going to be limited to 2 in the numerator. Actually, hang on. I'm actually going to write out that. I skipped a step when I shouldn't have. Give me 1 second. I'm going to write this out. So first, I'm going to add my denominator together. Oops. Yeah, 0.36 grams in the numerator. My denominator, when I add 1.00 with 0.36, the answer is 1.36 grams. Now look at the rules for sig figs for the denominator. We just added my last significant digit for 1.00 is in the second decimal place. My last significant digit for 0.36 is in the second decimal place. My answer has its last significant digit in the second decimal place, so I do not need to round or add any zeros. When I do the second step, I have 3 sig figs in my denominator. I have 2 sig figs in my numerator, so when I go 0.36 divided by 1.36, whoa, hang on. I got the wrong answer right at first. 0.36 divided by 1.36. Okay, well, I'm glad I redid this because my answer was wrong. So this equals 26.47058882. But I'm limited to the 2 significant digits in my numerator. So I count off my first 2, 4 rounds down. So my mass percent, or the percent mass of a saturated, excuse me, I'm so sorry. I tried not to hit the mic with that burst. I don't know if I was successful or not, is 26%. You'll notice that my units all canceled here. Grams cancels grams, which is good because we're getting a percentage. It shouldn't have units. And my final answer, saturated solution of sodium chloride has a percent mass of 26%. All right, so that's one type of problem you could see with mass percent. It's by no means the only problem type. You get served a problem that reads like the following. Brianna, you are sharper than I am today. So well done. I don't know what happened, but I probably punched in my calculator wrong. Is my best guess. All right, so let's take a look at this problem. A solution of potassium bromide has a percent mass of 14.0%. How many grams of potassium bromide are in 14.0 grams of solution? All right, now This is a little trickier and it takes a little more thought. The key here is you want to remember anytime you're given a quantity that has an equation, like we're given the percent mass here, it is in your best interest to write out the equation of percent mass because it will probably be useful in finding an answer to the solution. Here, actually, sorry, let's take this one step at a time here. First, let's identify what we're trying to find. Work this problem like every other problem. We want to find grams of KBr. All right, that's what we're after. Now let's talk about what we're given. And we are indeed given the percent mass, right? 14.0%. And whenever you're given a quantity that has an equation or is part of an equation, you should write out what that equation is. Percent mass is equal to grams of solute, which is, in this instance, KBr, over grams of solution times 100. So we want to find the numerator right here. We want to find grams of KBr. And you'll notice that we're given percent mass. We're also given something else. We're given grams of solution. We know that we have 14.0 grams of solution. That is our denominator. So we actually have enough information to solve for our mass of KBr. We just have to do a little bit of algebra first. So percent mass is equal to grams of potassium bromide over grams of solution times 100. We need to isolate grams of potassium bromide on one side of the equation. So we are going to put KBr in the denominator of this fraction. And no, we're not. We are going to put, because we want to solve for it, right? So we want to cancel grams of solution. That goes in the numerator. Then we're going to put 100 in the denominator so that the 100 cancels the 100 and the grams of solution cancels grams of solution. We also need to multiply it the same thing by the other side of our expression. All right, so now we have a new expression. Grams of KBr is equal to the mass percent times the mass of the solution over 100. We know what all of these quantities are, so we can plug them in. 14.0% times mass of solution, 14.0 grams over 100. So 14 times 14 divided by 100 is 1.96. Sig figs wise, we're golden, right? Both of these numbers in the numerator have 3 sig figs. Our answer is 3 sig figs. So a solution with a percent mass of KBr of 14.0% Um, 14 grams of that solution will have 1.96 grams of KBr dissolved within it. All right, we have one last percent mass problem to do, and I saved kind of the trickiest for last, the worst for last here. Or maybe it's the best for last. That'll be for you to judge. Let's take a look at the following example. All right, 44.0 grams of lithium iodide are dissolved in water to form a solution with a percent mass of 33.3%. What is the mass of water used to make the solution? All right. This problem's probably the hardest, but let's break this down. So first, just like any problem, oops. Let's go here. Let's identify what we're trying to find. We want to find the mass of water, right? Grams of H2O. Now let's look at what we're given. We are given that we have 44.0 grams of lithium iodide, right? That's our solutes. We're given the mass percent, which is 33.3. Right now, again, anytime you're given a quantity that has an equation, we should write that equation out. It'll probably be useful. The equation for percent mass is equal to the grams of the solute over grams of solution times 100. All right, now if you look at what we have, we've got percent mass. We also have our mass of solute. So what does that allow us to find here? Well, it allows us to find, we could algebraically solve for the mass of the solution. But the mass of the solution is not the mass of water. Those are two different things. But hang on a second. Grams of solution has an equation. When we were writing out the expression for percent mass right at the beginning, we said that the mass of the solution was equal to, or here, hang on, I'm going to go with a different arrow. This is going to be cleaner. we said the mass of the solution was equal to, hang on, the grams of water plus the grams of solute. We know what this is. We want to find, this is grams of water. That's what we're after in the first place. So if we can find our mass of solution, then we can use this equation to solve for mass of water. So this is going to have two steps to it. First, we're going to use the equation for mass percent to find the mass of solution. Second, we're going to use this expression to find our mass of solvent. This is going to be a lot of algebra, so I'm just going to clear the board and take it one mathematical step at a time. So our percent mass is equal to grams of lithium iodide over grams of solution times 100. We need to solve for grams of solution, so we're going to multiply both sides by our solution's mass. Mass of solution cancels. We get a new expression. Mass of our solution times our percent mass equals mass of lithium iodide times 100. Now we want to solve for our solution's mass, so we're going to divide both sides of this equation by our mass percent. Mass percent, cancels, and we get a new expression. Grams of solution are equal to grams of lithium iodide times 100 over percent mass. We know all three of these quantities, so we can plug them in, and I will up here. Our mass of lithium iodide is 44.0 grams times 100 over our percent mass, which is 33.3. So 44.0 times 100 divided by 33.3 gives us our mass of solution is equal to 132.132. Well, isn't this a fun number? Because that just repeats. Grams. Sig figs wise, we're limited to 3 by both numerator and denominator. I'm going to wait to round because this is not our final answer. This is just our mass of solution. But I'm going to use the whole number, but I'm putting these lines here to remind myself that this number only has 3 significant digits. All right. Now we're not quite home free, right? We know our mass of solution now, and this is good because we need to use this expression. Mass of solution is equal to mass of water plus our mass of lithium iodide. So we can solve for our mass of water if we subtract the mass of lithium iodide from both sides of this expression. This gives us a new expression. Our mass of water is equal to the mass of our solution minus the mass of lithium iodide. Our mass of our solution we just found was 132.132 grams, 3 sig figs in this number, minus our mass of lithium iodide, 44.0 grams. So 132.132 minus 44.0 gives us 88.132 grams. Sig figs wise, we're subtracting here. 44.0 has its last significant digit in the first decimal place. However, 132.132 has its last significant digit in the ones place. So the ones place is where we've got a round to, and 1 rounds down. So our answer is 88 grams of water were used to dissolve 44.0 grams of lithium iodide. That's about as rough as they come when it comes to percent mass problems. Okay. Now, this is just our first concentration unit. But don't worry, they all will not take this long. Our next concentration unit is very closely related. And it is a concentration unit called, oops. There we go. Called percent by volume. Or I should say, here, hang on. Percent volume, just like percent mass is abbreviated percent M over M. This is percent V over V. And the equation for percent volume is equal to the volume I should say it's not just the volume, the milliliters of solute over the milliliters of solution times 100, just like with percent mass. Right here, these milliliters of solution are equal to the milliliters of solvent plus the milliliters of solute. Now, honestly, percent by volume is not super common. You need to be aware of it. It could show up in a problem, but the math is exactly the same as percent by mass. It's not as common, so I'm not going to do an example with it. Honestly, where you see this most frequently is with alcohol. So when you see like beer, like a beer would be like, 4 to 10%, or wine would be like 15 to 20%, or liquor, depending upon your poison of choice, would be between like 40 to 50. The higher ones are 50. Those are all percent by volumes because you're mixing ethanol with water. So you have a liquid solute and a liquid solvent, and that's why percent volume is commonly used there. In at least the chemistry that I've done, I've never run across a percent by volume. It's always been percent mass, or the next one we're going to talk about, which is percent mass to volume. All right. Now, percent mass to volume is equal to the grams of solute over the milliliters of solution. Something that should be pointed out here is if if the solid, or sorry, if the solute is a solid, then milliliters of solution are just milliliters of solvent. All right. On the other hand, if the solute is a liquid, then milliliters of solution is equal to milliliters of solvent plus milliliters of solute. The reason for that is a solid solute, when dissolved in a liquid solvent, doesn't add to the volume. So the volume of solution is equal to the volume of solvent unchanged. But a liquid solute does add to the volume of solution, so that's why you have to keep both of them in play if the solute is liquid. But often you'll see this written, solid solutes are so common and are much more common than liquid solutes that often you'll see percent mass to volume written as grams of solute over milliliters of solvent. Can't forget to multiply by 100 right there at the end. So this one actually sees more play than the other. So it's not uncommon to see this one used. And actually, now that we know this concentration unit, it allows for some interesting examples like the following. A solution of potassium chloride has a percent by mass of 19.0% and a density of 1.012 grams per milliliter. What is, or I should say, find the percent mass to volume for this solution. This may seem very challenging because you've never done a problem like this before. This makes it the perfect example, a perfect simulation for the exam, because you will see problems on the exam that I have not done in lecture, that you've not done in your homework. So, this is why this is the perfect scenario to practice for that. Because what you want to do in that situation, when you read a problem, you're like, I've never seen this before on the exam. Don't panic. Start by writing down what you're trying to find. We want to find percent mass to volume. Awesome. Write out the equation. This is equal to grams of solute over milliliters of solution times 100. Let's look at what we're given. We're given the percent mass, right? is 19.0%, and we're given the density is 1.012 grams per milliliter. Now you may look at this and be going, okay, Josh, I don't see a way forward. Here's a useful trick with all of these percent concentrations. And I want to demo it here with percent mass. I want you to think about what this 19% means. All right? This means that you have 19.0 grams potassium chloride in 100 grams of solution. Right? That's what that 19% means. That means in 100 grams of solution, our denominator, we have 19 grams of solute. Notice that we already have grams of KCl in a numerator. That's what we want. If we want to find percent mass to volume, we want grams of solute in the numerator. Let's look at the denominator. We want milliliters of solution. What do we have? Grams. If only there were some way to convert grams of solution to milliliters of solution. Wait, hang on. What is with this density? This density tells us that our solution has 1.02 grams per milliliter. This is grams of solution to milliliters of solution. So we can actually use our density to do our dirty work, to do this conversion for us. Grams of solution cancel grams of solution, leaving us with milliliters. Let's crunch our numbers. 19.0 divided by 100 times 1.012. Actually, hang on, before we crunch our numbers, remember, percent mass is a percentage. That means we have to multiply by 100. So now that we have grams of solution over milliliters of solution, you got to multiply by 100 to get it into a percentage. So the percent mass to volume of this 19% by mass solution of potassium chloride is, let's see, we got to round to 3 sig figs, 19.2%. And that is how you solve that situation. The important twist is remembering what the percentage by mass means. It was grams of potassium chloride over 19 grams of potassium chloride over 100 grams of solution, and then moving forward from there. You'll see that trick again before we leave this chapter. All right, in our closing few minutes, I would like to take a moment and set up what will be a rich discussion of our last concentration unit of the chapter. And this is the preeminent concentration unit, the most important concentration unit that you will be dealing with. And that concentration unit is molarity. Molarity is abbreviated with a capital M. Oops. And the equation for molarity is molarity is equal to the moles of solute divided by the liters of solution. All right, that is the definition for molarity. Something you should be aware of. How to pronounce this, how to verbalize it. So if you had 0.10 molarity of sodium chloride, you don't say molarity. It's kind of awkward to say. You say molar. So if I were to read this, this would read as 1.0. This is, or sorry, hang on. This is a 1.0 molar solution of sodium chloride. All right, that's the compact version, 1.0 capital M NaCl. If I'm reading that off the page, I read a 1.0 molar solution of sodium chloride. That's how you kind of pronounce it and verbalize it. Now, this is the preeminent concentration unit because it has moles in the numerator. And if we have moles, we can do stoichiometry. We're going to be doing a ton with this unit before the semester is done. So I don't want to dive into a new example. There's only 5 minutes left in lecture, so we're going to call it a day there. But we'll come back on Tuesday and dive in with molarity. Again, lab tonight is just office hours, so drop by if you have questions about the lab or anything else. I'm here and ready to hang. All right, I'll catch you guys all in a few.